Hey everyone, it's Mr. Corvin. Today we're going to be talking about Chapter 11.3, which is the integral test and estimates of sums. So we're moving, we've been talking about sequences and series. We talked about whether a sequence converges or diverges, and then we talked about whether a series converges or diverges. And in many cases we were able to say what the series converged to. But we were only able to do that for some very specific situations where we were able to find a formula for the sequence of partial sums of the series. So that doesn't always work. Like, that's very difficult to do in general. So kind of the next phase of this, which is going to handle a couple of different methods, is we're going to be talking about tests that we can do to say whether a series converges or diverges without necessarily being able to say exactly, oh, I know it converges to this sum. All we'll be able to say is it converges. We might be able to give a boundary on it, but we won't be able to say exactly what it converges to. So that's sort of the next step of where we're going. So this is going to be the first of many tests. In fact, the next several chapters will all deal with various tests for convergence and divergence of infinite series. All right, so as I was saying, that in general, finding the exact sum of a series can be very difficult. And so with geometric series, we had a formula, which was a over 1 minus r, assuming that the absolute value of r was less than 1. We also looked at the series 1 over n times n plus 1. We were able to do a partial fraction decomposition. It was a telescoping series. So we were able to find a closed form formula for the sequence of partial sums. Okay? In general, that's very difficult to do. In general, we can't do that. So then the question becomes, what do we do in order to make sure that we can say whether this series converges or diverges? So we're going to start by looking at an example. We're going to look at this sequence, which is the sum from, or excuse me, the series, which is the sum from n equals 1 to infinity of 1 over n squared. So this is a series whose terms are the reciprocals of the squares of positive integers. Okay, so my iPhone thought I was asking it a question because I said the word series and it heard Siri. So that was funny. So that's why I had to reach over for a second and turn that off. All right, so we have 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared, etc., etc. So the question is not even the first question is, does this series even converge? Does it come to a finite value? And then once it does, we could, look and ask ourselves, well, what does it converge to? Which turns out to be a very complicated question, and one that we actually don't address in this course. This one they do actually know the sum of the infinite series. All right, so one thing you can do in terms of investigating is just making a table. So that's what they've done here. They said, let's look at the sum of the first 5 terms, 10 terms, 50 terms, 100 terms. And it's increasing, as it makes sense, because each time we're adding on some more. But it seems like it stops increasing rapidly, and it seems to be converging to somewhere around 1.64, 1.65, somewhere in between those two numbers. It appears to be converging there. And that's what the table says. So the problem is, how do we prove it? Because the harmonic series, it seemed like, hey, maybe that's converging, but then we showed that it diverges. So how do we deal with this? And there's no simple formula for the sum of the first n terms. There is not for this one. All right, so what do we do? Well, we're going to actually model it using an integral. So what we're going to do is we're going to look at the function 1 over x squared. And then what we're going to do, hold on 1 second. There's my pen. Yep. All right, so we're looking at the function y equals 1 over x squared. And what we're going to do is we're going to take the function value at every integer. So that's 1, that's at 2, that's at 3, that's at 4, and that's at 5, so on and so forth. Okay, and the idea is that we can model this with a rectangle. So the width of all these subintervals is going to be 1, and then the height of the function gives us the term of the series that we'd be adding. So if we add up the area of all of these rectangles, so here's the first one, here's the second one, here's the third one. If we add up the area of the rectangles, we get the sum of the series. Okay. Okay. So we know that those two are equal. So in essence, we're going to be looking at a sum of areas. And when you think sum of areas, particularly with a function, the first thing you might think of is a Riemann sum. This is a specific Riemann sum, but the problem is we can't take the number of subintervals to infinity. That's not actually what we're looking to do here. But we do want to get the idea of an integral. So if we start by looking at 1, right at the point 1 comma 1, which is right here, and I'm going to change pen colors for a second. I'm going to change it to green. Okay. I'm going to ignore that first one for a second, and I'll explain why in a moment. But if we look at the total area under the curve from 1 to infinity, clearly that's bigger than the sum of the areas of the rectangles if we ignore the first one. So I'm going to say that 1 plus the sum of the areas of the rectangles okay, because I took out the first rectangle. But we can see that if we did the integral, there's some extra area that the integral is going to capture that the other piece did not. 1 plus the areas of the rectangle starting from n equals 2, I should say. So I should clarify there. So I'm ignoring the first one. So that's going to be clearly strictly less than 1 plus the integral from 1 to infinity of 1 over x squared dx. Okay. So what I'm doing is I'm comparing the areas of the rectangles to the value of this indefinite integral. Or excuse me, not indefinite integral, improper integral. So we can actually do this. So we know that the sum from any, well, I mean, we can get all technical, and this will be on the next slide. But essentially, we know that the antiderivative of 1 over x squared is negative 1 over x, and we can do the limit as, make a new variable as x goes to, or t goes to infinity, and then substitute in 1. And what we'll see is that this improper integral converges. So what I have is, I have a sequence of partial sums that is increasing, because each time I go further in the list of partial sums, I'm adding something to it. And this expression right here gives me an upper bound. And obviously 0 is a lower bound because it's positive. So we actually are going to be able to say something about that. So we have the sum of the areas of the rectangles. We exclude the first rectangle. The remaining rectangles is smaller than the area under the curve. And as you can see, the improper integral converges to 1, so that the sequence of partial sums is bounded above by 2. So we know that the sequence of partial sums can never go over 2. So I have a sequence of partial sums for this series that's increasing and bounded above. And we can also say it's bounded below by 0. So it's increasing, it's monotonically increasing and bounded. And by the monotonic sequence theorem, we can then say that that sequence converges. Okay, so you have to remember the monotonic sequence theorem. Monotonic sequence theorem says if a sequence is monotonic and bounded, it must converge. All right, so we had a monotonic sequence. The sequence of partial sums was increasing. It was bounded above by 2. It was bounded below by 0. Therefore, I can say that the sequence of partial sums converges. And since the sequence of partial sums converges, the series also converges. Now, all I can say is that it converges to something less than 2. Well, greater than 0 and less than 2. I can't say anything else beyond that. But that's enough. That's enough to say it's convergent. And that's all that they were asking for. They just want to know, does it converge? Because in reality, if you have some sort of application where this came up, at some point you just need an answer to a certain level of precision, and we're going to talk about that a little bit later in this chapter. So it doesn't, getting the exact value is not really that important. You just go, oh, I need 6 decimal place accuracy, and then you say, okay, great, I need to do this many terms. That's 6 decimal place accuracy, close enough. All right, so now we're going to look at a new series, very similar setup. This is the sum from n equals 1 to infinity of 1 over the square root of n. So basically this is the same setup. Oh, I also just want to mention really quickly one thing that I just realized. Why did we have to take out this first term? So the reason we had to take out this first term is because if I didn't take out this first term and I wanted to say something about the areas of the rectangles in terms of an integral, I would actually have to go from 0 to infinity, and the problem is that that improper integral does not converge, because if you go to 0, it does go, the area goes infinite as you get closer to 0. So that's why we weren't able to do that. But remember, you're always allowed to take out like the first couple terms if maybe they either don't follow the pattern or something weird happens. And so this is an example of that. This is one of those reasons why we want to be able to say, okay, I need to take out the first term of this sequence, and then I'm going to say something about the rest of it, or the first term of the series, and say, I'm going to say something about the rest of the series. And if it's true for the rest of the series, then I don't care about those first couple terms. So that's a very important thing to note. All right, so let's take a look at this series. So this is the reciprocals of the square roots. And we're going to do the same thing. We're going to start by investigating. But this time, as we start to go up in n, we notice that it just seems to kind of keep getting bigger and bigger and bigger. It doesn't seem to be approaching anything. Whereas before, the way it was growing was really slowing down. I mean, here the rate of growth is still slowing down, but it doesn't seem like it's going to stop. Right? So we can see, you know, with 1,000 terms it went up to 61.8. With 5,000 terms it went up to 139.9. That's nearly 140. It just doesn't, there's no evidence that it's going to converge to something. So our suspicion might be, hey, this might be a harmonic series situation. And if you sort of just think about it and you go, well, I'm taking the square root of all the denominators, that's making all my denominators smaller than the corresponding terms of the harmonic series. And if I make denominators smaller, that makes fractions bigger. And if I make fractions bigger, if I make something bigger than something that I already know is diverging to infinity, then that thing is also probably going to diverge to infinity. We're actually going to talk about that more explicitly in the next chapter, or possibly the one after that. But that's sort of an intuitive argument. Another interesting way you can think about it is say, okay, well, what if I just take the terms whose denominators are perfect squares? Well, then I have 1. And then if I take 1 over root 4, that's 1/2. If I take 1 over root 9, that's 1/3. If I take 1 over root 16, that's 1/4. If I ignore all the other terms and just take those terms, I get the harmonic series, and I know the harmonic series diverges. And then I'm just adding more into it, so we know that this is going to be a divergent series. So that's sort of the intuition here. But I would like to be able to say something a little bit more explicitly. I'd like to do something like I did for the 1 over n squared series. So we're going to do the same thing. We're going to set up an integral, except this time we need to set up a divergent integral, and our series needs to be greater than the divergent integral. So here's our picture. So now we have the function y equals 1 over root x. And here the difference is that we've set things up so that the tops are above the curve. So that means the area of the rectangles is actually greater than the integral. And here we don't have to ignore the first term. So the sum of the areas of the rectangles is greater than the integral from 1 to infinity 1 over root x dx. Okay. All right. And so now the height, we're using the left endpoint here so that the tops lie above the curve. Whereas before, you may have noticed we used right endpoints so that the rectangles lay below the curve. Okay, so the sum of the areas of the rectangles, which is the sum of the series, is greater than this improper integral. And if this improper integral diverges, then the series also diverges. And you can see pretty easily this comes out to 2 root x, I believe. Yeah, 2 root x, because then that cancels. And when you plug in infinity, which you can't, you take the limit as t goes to infinity, that's infinity. You're done. Okay? And so this improper integral diverges, therefore the area under the curve is infinite, so therefore the sum of the series is infinite, which means the series diverges. Okay, so we've now made this connection between an integral converging or diverging and a series converging or diverging. And we use some very simple series to kind of get the idea. But in reality, it works for any series as long as it meets some basic conditions. All right, so this is known as the integral test. So this is very important here. So we need f to be a continuous, positive, and decreasing function on the interval from 1 to infinity. And we're going to let the sequence a sub n be f of n. Now, in reality, we usually start with the sequence a sub n that's going to lead into the series, the sequence of terms that we're adding up to get the series. And then we make our function based on that. The key thing is you're checking to say, if I replaced n with x, do I get something that's continuous, positive, and decreasing? If it doesn't meet those criteria, then you can't use the integral test. This is nice because of the next sentence. It says, the series sum from n equals 1 to infinity of a sub n is convergent if and only if the improper integral from 1 to infinity of f of x dx is convergent. So it's tying the convergence of the integral to the convergence of the series. They are linked. So if the integral is convergent, then the series is convergent. If the integral is divergent, the series is divergent. And this is really helpful because doing improper integrals is pretty easy. Most of the time. Obviously, there are sequences, that you might be adding up where the integral isn't very nice to do. Maybe we're dealing with some factorials, maybe we're dealing with some things that aren't continuous functions, or that aren't easily expressed as continuous functions, using methods that we learn in this class. And then you can't use the integral test for that. But this is going to lead us to a very, very nice alternative statement that we're going to be able to use for some of the other tests as well. So this is the first test for, other than the divergence test, which we learned about. This is a test that we can use. This is called the integral test. All right, so let's take a look at this example. We're going to look at the series from n equals 1 to infinity of 1 over n squared plus 1 for convergence or divergence. So we're going to use the integral test for this one. And basically we're going to say, okay, if I replaced n with x, so I have 1 over x squared plus 1, is it continuous? Yes, it is continuous from 1 to infinity. It's actually continuous everywhere. Is it positive? Yes, it is always positive. The denominator is always positive, so we're good. Is it decreasing? Okay, well, technically there's something to check there. We do want to check to see that that's decreasing. That's pretty easy to verify, that it's always decreasing on the interval from 1 to infinity, because as x increases, the x squared is going to increase, so the denominator is going to get bigger, which means that the fraction is going to get smaller. All right, so we are set up to use the integral test here. So let's see how we're going to set that up. As I said, it's continuous positive decreasing, so we're going to look at the limit as t goes to infinity of 1 to t, 1 over x squared plus 1 dx. So we're going to take a look at this improper integral. If it converges, then the original series converges. If it diverges, then the original series diverges. So you may recognize this. This is one of our special integrals. This is arctan x. So we're doing the limit as t goes to infinity of arctan x from t to 1. And we see how we evaluate that. Plug in t, plug in 1. Arctangent of 1 is pi over 4. And as t goes to infinity, the arctangent of t is, goes to pi over 2. So we get pi over 2 minus pi over 4, which is pi over 4. Again, the exact value doesn't matter so much. What matters is that it converges. So in this case, the improper integral converged. So by the integral test, we can say that the original series converges. And we can say that it converges to something that is, you'd want to look at the, just like the exactly how you set it up and everything. You can't, it doesn't quite converge to, oh, it's something less than pi over 4. You can't directly say that because of, again, that first term is in the wrong spot. So first term plus pi over 4 is going to get you something that it is going to be the bound. But again, integral test, we don't actually care what the bound is. We just care if the integral converges, the series converges. If the integral diverges, the series diverges. Okay, this is a super important series. This is called p-series. When you have the series from n equals 1 to infinity of 1 over n to the p, that is the p-series. We actually already looked at this as an improper integral. So we already looked at this going from 1 to infinity, or from any number greater than 0 to infinity. And what we found was that the integral converged if p was greater than 1, and it diverged if p was less than or equal to 1. So we actually proved that just doing the improper integral out. Well, if we apply that knowledge along with the integral test, we get this theorem right here. So this is one of those things that's just really good to have memorized. You're not expected to say that whole thing about the integral test or actually do the improper integral. This is just the p-series test. So the p-series from n equals 1 to infinity, 1 over n to the p, converges if p is greater than 1, and diverges if p is less than or equal to 1. Notice that when p equals 1, that's the harmonic series. So this provides us this really important baseline. So we had this question of, okay, the harmonic series diverged, 1 over n squared converged, where is that dividing line? It turns out 1 is the dividing line. Turns out p equals 1 is the dividing line. Okay. So here's some examples. I have the series sum from n equals 1 to infinity, 1 over n cubed. It's a p-series with p equals 3. 3 is greater than 1. Series converges. Done. End of story. Do not need to say anything else. Here we have 1 over n to the 1/3, which is the same as 1 over cube root of n, sum from n equals 1 to infinity. It's a p-series. P is 1/3. 1/3 is less than 1. It diverges. Done. End of story. Everything we've done in the video today is consistent with this fact about p-series. Okay? Alrighty. Alright, so now here's another one where we're going to have to use the integral test, so it's not a p-series. Again, you can kind of use some intuition here. This is not the only way to handle this particular series, but we're going to look at the series, the sum from n equals 1 to infinity of natural log of n over n. does it converge or diverge? So if you ignore the first two terms, this is always a sequence. The terms of the series that we're adding up are always bigger than the corresponding terms in the harmonic series. So except for the first two. Because in the harmonic series, the numerator is always 1. And so once you get past E, so 3 and up, you get things in the numerator that are bigger than 1. So those are bigger than the corresponding terms in the harmonic series. So that leads us to this idea of, hey, this probably diverges. Because it's related to, it's bigger than the harmonic series. But we can do this with an integral. So we have to make sure we can use the integral test. Is natural log of x over x positive? Yes. So for x, when x equals 1, it's 0. After that, it's positive. Is it continuous? Yes, the logarithmic function is continuous. So we're all good there. We avoided dividing by 0. Is it decreasing? So here's where things get a little tricky, and you might actually have to do a derivative to show that it's decreasing. And that's required to use the integral test. Though if it isn't decreasing, then we have some other problems. Okay, so in order to check whether or not the function is decreasing, we look at the derivative. So using the quotient rule, we compute the derivative as f prime of x equals x times 1 over x minus natural log of x over x squared, which simplifies to 1 minus natural log of x over x squared. So the question is, when is that negative? That is negative as long as x is greater than e. So the denominator is always positive. The numerator, like I said, for the first two terms, that's still positive. So natural log of 1 is 0, so positive there. Natural log of 2 is less than 1, so still positive there. Once you hit e, then it goes negative. So the derivative is decreasing once you get past e. And again, this is that convenient thing. We can ignore that the first two terms, it kind of doesn't work. We can just throw those out. So we're good there. So f prime of x is negative when natural log of x is greater than 1, so x is greater than e. So that means we can apply the integral test because we got that it was eventually decreasing. And in order to do this, you can do a u substitution. U equals natural log of x, du is dx over x, so it's natural log of x squared over 2. That's a basic u substitution there. You substitute in t and 1, and as t goes to infinity, natural log of t also goes to infinity, so this whole thing goes to infinity, and there's another argument that this is a divergent series by the integral test. So as you may have noticed, sometimes the integral test, technically, it worked here, but it seemed like there was a lot of extra work that had to happen along the way. That's true frequently with the integral test. There are other tests that are a little bit more intuitive. I kind of mentioned just comparing it to the harmonic series and saying this series is greater than the harmonic series. We know the harmonic series diverges, therefore this also diverges. So this is the first test that we're learning, but it's not the only test we're going to learn. There are often multiple ways that you can prove the convergence or divergence of a series, and you just have to use the one that makes the most sense to you for that particular problem, or is easiest for you to use for that particular problem. This one, doing the integral, you have to do a u substitution. You have to take the derivative in order to prove that it's decreasing. There are some good reasons right there that say, hey, maybe I shouldn't be using the integral test here. That's probably not the easiest way to do it, but it does work. All right, so now the question is, can we use the integral test to actually help us estimate the sum of a series? And it turns out that we can. All right, so let's suppose that we've done the integral test. We know that the series is convergent. We want to find an approximation for the sum. Well, the first thing is, hey, like, the integral seems like it might be a good approximation for the sum. Yeah, I mean, it's a bound, so it's an approximation. But any partial sum is also an approximation. So what we really want is we really want something where we can say, hey, like, how many terms do I need to get a good enough estimate? So this is very similar to what we did with approximate integration, using the midpoint rule and the trapezoid rule and Simpson's rule. So we're going to kind of do something a little similar here. And I'm going to show you how that works. So what we're going to do is we're going to start by defining the remainder of a series. So the remainder, Rn of a series, is defined by the actual sum of the series S minus the nth partial sum S sub n. Okay? So this is all the terms, the sum of all the terms past A sub n. So that's Rn. That's the remainder. And what we want is we want R sub n to be really close to 0. If we can say, hey, I know that R sub n is less than this, then that tells us how accurate our nth partial sum is as an approximator. Okay? So the idea is, well, hey, like, I can approximate the sum of the terms from n plus 1 to infinity with an integral. Actually, and I can do it two different ways. So what we see here is we see this lovely little picture. So here we're doing the integral of f of x from n to infinity, and we see that Rn is less than that. So Rn is the sum of all these rectangles, and we see that it is less than the integral from n to infinity. But then if I just shift it over, I'm just going to shift everything over 1 unit to the right. And then when I shift everything over 1 unit to the right, we get a series of rectangles that lie above the curve. So this also represents Rn. We know that Rn converges, because we know that the series converges. And we're saying, well, hey, I know that Rn is bigger than the integral from n plus 1 to infinity. So that's what these... that's what all these equations right over here are saying. So we're getting both an upper bound and a lower bound for R sub n. If I can get an upper bound and a lower bound for R sub n, like, that really helps me bound R sub n, and that's pretty awesome. Sometimes only the upper bound matters, like, particularly if it's just I need to know that am I within 3 decimal place accuracy, so is R sub n less than or equal to 0.0005? Yeah, you just need the upper bound there. But the fact that we can get a lower bound as well is not unhelpful. So this is called the remainder estimate for the integral test. And basically it just says everything I just said, which says that the remainder R sub n is bounded between the integral from n plus 1 to infinity of f of x dx and the integral from n to infinity of f of x dx. We are assuming that f is a continuous positive decreasing function for x greater than or equal to n. We are assuming that the whole series is convergent. So that's an assumption that we've already made. And then Rn is defined as we've defined it there. All right, so that's the remainder theorem. The more important part of this equation, where are you, pen? There it is. Oh my. Will that erase? Oh no, go away, back. There we go. Sorry. All right, so the more important part is this part right here. This is the more important part, because the upper bound is more important than the lower bound. Excuse me. And just as a reminder, this is the how good our estimate is if we just use the first n terms. I mean, the other thing is, like, you can estimate the sum of the whole series by just saying, I'm going to add Sn to everything here, and then you actually, that is useful too, to say, oh, yeah, it's going to be between this and this. So we're going to take a look at this example. We're going to look at the sum of the series sum from n equals 1 to infinity 1 over n cubed. We're going to use the sum of the first n terms, so S10, and then we're going to estimate the error involved. And then B is really the more important question. So let's take a look at B. How many terms are required to ensure that the sum is accurate to within 0.0005? So that's 3 decimal place accuracy. That means that I am correct. The first 3 decimal places are definitely correct. All right, so we're going to do the integral from n to infinity of f of x dx, and we're just treating it with n. We're just going to say it's from n. So we do that, and we get this lovely thing, t equals, limit as t goes to infinity, negative 1 over 2x squared from t to n. That's just doing the integral. And hey, as t goes to, well, let's actually do it now first. So we have negative 1 over 2t squared plus 1 over 2n squared. Well, hey, as t goes to infinity, that part right here, there it is. That goes to 0 as t goes to infinity. The other part doesn't involve t, so 1 over 2n squared is my remainder estimate. Okay, so that's my upper bound on the remainder. So if t equals, or excuse me, if n equals 10, if I'm estimating with the first n terms, I can say that I'm within 1/200th of the actual sum of the series. All right, so that's the approximation. So the approximation, they just added up, they just took the first 10 terms, and then according to the remainder estimate, R10 is less than the integral from 10 to infinity, which is that, which is 1 over 200. So basically, I know that the sum of the infinite series is about 1.1975 with error less than or equal to 1 over 200. Okay, so the size of the error is at most 0.005. So this is a 2 decimal place accurate. This is 2 decimal place accurate estimate because the size of the error was 0.005. All right. So I know it's 1.19 something. I don't know about that 7. That 7 could be sketchy. Who knows? Probably is sketchy. Yeah, no, I'm correct within 2 decimal places. Well, okay. So by correct within 2 decimal places, that means with rounding. So technically, it's like I'm correct in the sense of like it could be 1.20. If I rounded this to 2 decimal places, then 1.20 is a correctly rounded 2 decimal place estimate. All right, so now let's look at part B. Part B, that means my error term needs to be less than or equal to 0.0005. So essentially, we're saying that 1 over 2n squared has to be less than 0.0005. This is exactly like we did before with the other error bounds for Simpson's rule and the midpoint rule and the trapezoid rule. We're just going to solve this for n. Okay, so when we solve it, we get this, and it turns out that n has to be greater than 31.6, which means that we need 32 terms. So to ensure our 3 decimal place rounded accuracy, we need 32 terms. Okay, and that's how this theorem works. All right, just the last thing, as I said before, if you add Sn to everything in that inequality, you get the sum of the series. So this lets you kind of like narrow in on what the actual sum is with both a lower bound and an upper bound. But in terms of accuracy of using the first n terms as an approximation, you really only need that upper one. Okay. Also, just to be clear, like using these expressions gives a more accurate approximation than just using the partial sum. It's not like, you know, like I said, it's not really that critical. We don't usually really care what the sum is. We just need to say, okay, how close is close enough? Okay, I think that should do it. That does it for chapter 11.3, which is the integral test. So just to recap, we learned about the integral test. So I'm going to go back to that slide. Should probably just Takes a long time to scroll back. There it is. Okay. So just to recap, the integral test says that if we have a continuous positive decreasing function, that our series, the terms of the sequence that we're adding up for our series, if those are if when I write that as a function, it's continuous positive and decreasing from 1 to infinity. Again, it can be from something else to infinity if we need to ignore the first couple terms. Then the improper integral and the series will either both converge or both diverge. So that's main point number 1, is that the improper integral tells you whether the series converges or diverges based on whether the improper integral converges or diverges. And then the second part was the p-series test, which if you have a p-series, it converges if p is greater than 1, and it diverges if p is less than or equal to 1. And then we kind of explained a little bit why that was true. And then finally, we took a look at the error bound using improper integrals to help us bound the remainder term, which will help us find how good our estimate is. And so the key equation there was this one right here, and then particularly the second part of that inequality is the important one. Right, so I hope that this was helpful for you. Please do make sure to check your email on Wednesday before class, just in case there are any updates, if there's another video that will be posted, or if something happens. And please feel free to email me if you have any questions, comments, or concerns. But I do thank you so much for paying attention, and I hope you have a great rest of your day.